We present improving graph networks through selection-based convolution. Graph convolution is often formulated as a message-passing algorithm, where each node has values or features associated with it. During the convolution, those node features are multiplied by some learned weight. Then every node looks at the features of its neighbors and aggregates them in some permutation invariant way, leading to a new value for the node in the following layers of the network. While this approach works, it does not allow for any distinction between the nodes. They are all treated the same way. In contrast, if you compare it to image convolution, for example, neighbor pixels are given different weights based on whether they are above or below the center pixel, to the left or to the right, etc. However, when graph networks operate on position data, nodes may be above or below each other, but this information can only be included as node features that have to be learned on. Graph data often has intrinsic relationships, such as spatial relationships, where nodes have direction and distance relative to each other, or temporal information, where dynamic graphs are involved and the nodes are changing over time. Edge properties, such as bond types in molecules, or multimodal data, where you're connecting edges to different types of data, or even user-specified properties that may be in the data itself. So what if you could apply different learned weights to each node based on their specific relationship to the current node? This would allow the neighbors to pass unique messages in the graph convolution, just like in image convolution. In order to do this, we propose selection-based graph convolution. It builds on our previous work of selection conv that focused on images, but modifies the approach to work for graph problems. It preserves intrinsic relationships by pre-processing the edges of the graph into multiple groups that we call selections. Each selection has its own unique learned weights in the graph network. This description may remind you of other approaches that have been applied to graph convolutions, so let's clarify what is new in our approach. Previous approaches have applied variations to the following standard setup. The network multiplies each neighbor by the same weight, and then applies a permutation invariant function to aggregate them. The network may have fixed edge weights between 0 and 1 to indicate the amount of influence between a source and target node. It may also have learned edge weights, using mechanisms like attention, but those weights still generally stay between 0 and 1. Overall, this structure loses intrinsic relationship information because relationships cannot be encoded in the edges. They have to be encoded as node features and learned on in the network. In comparison, our approach does the following. It partitions the edges into groups called selections as a pre-processing step. Then it multiplies neighbors by a unique weight based on its assigned selection. In this case, the edge weights are learned for each selection, but in comparison to other approaches, they can be positive or negative and can be different for each channel. They're no longer fixed between 0 and 1. Overall, this structure keeps the intrinsic relationship information in the edges themselves, leading to faster convergence and better performance. Let's look at how you can simply add selection into graph networks. Consider the following graph convolution function as presented by Morse et al. It multiplies weights to neighboring target node features and then adds them to the source node. To add selection, you simply have to add another summation, where the second summation is over selection weights. So each target node feature will have a unique selection weight applied to it based on its selection value, and then it is aggregated. We can do this for any graph network that uses a message passing system. You can write message passing as a generalized equation, and selection can be simply applied to that equation by, again, summing over selection weights in the message pass. So just like there are various kinds of intrinsic relationships in the graph network, we can write unique selection functions for each kind. They can be spatial selection functions, or distance-based selection functions, time-based, or a combination of properties that the node features may have, or even act on edge features. Overall, they can be custom designed to fit whatever kind of data you are working with, as long as you know how to separate them into groups based on the initial graph structure. So let's look at some examples of where this can be applied. The first example we looked at was superpixel graphs. We experiment with the MNIST superpixel dataset, where each image in MNIST is broken into superpixels and then represented as a graph by taking the centroids of each of those superpixels and connecting them. We wrote a selection function that looks at direction and processes each edge based on the direction of the source to target node. By adding the simple selection function and applying unique learned weights to each one, we found the following. First of all, we could take standard networks that are often used for tasks like this and we could greatly improve the final accuracy by incorporating that selection. Additionally, we found that they quickly converged when that information was provided. A second example we can look at is 3D expression recognition. We used the COMA dataset, which contained 3D meshes of various spatial expressions. We used a 3D selection function that processed each vertex in the mesh and determined the direction to each target node relative to each source node. When we added this selection to various graph networks, we found that the accuracy again improved for many standard networks. We also found that it outperformed GATT, which we often think of as learning these intrinsic relationships indirectly. We even approached accuracy of networks that are specifically designed for 3D data. Another example we can look at is traffic prediction. We looked at the meter LA dataset, which has over 200 sensors in the LA area, and records the traffic speeds at various times throughout the day. We used a distance-based selection function that separates target nodes into groups based on how far away they are from the source node, since it is likely that future traffic speed is dependent on how far away cars are currently from a given location. To add selection to this, we decided to use the temporal backbone of AT3 GCN, and then add selection to the spatial aggregator function. We found that this network that normally does not do well on the dataset quickly improved with selection as the spatial aggregator. It outperformed all the other spatial aggregators that we tested, and its performance improves as the network gets deeper, unlike the other aggregators. This is because selection can apply a nonlinear piecewise function across distance because of the different partitions, whereas other networks are unable to do this with their current representation. We even found that this simple addition to the network made it comparable with state-of-the-art approaches that are applied to this task. Last of all, we looked at molecular property prediction. We processed the QM9 dataset, which has various organic molecules, and the task is to predict properties of those molecules. We chose to use a selection function that was custom designed that looks at angle between triplets of nodes, since DimeNet, a common network that is applied to this task, already processes this information. By adding selection into the network, we found the following. For the various properties that are predicted for the molecules, when you compare to the original DimeNet, we found that you can either improve the performance with a very similar network, but just adding selection to it, or you can use a much smaller network and get similar performance to the original by incorporating selection into it. In conclusion, we have shown that selection-based graph convolution provides a way to incorporate intrinsic relationships into the network. When these intrinsic relationships are known and a selection function can be designed and selection-based convolution is used, it leads to faster convergence during training, improved final testing accuracy of the network, and similar performance while using networks of smaller size and simpler design. Thank you.